This video is about the expectation and the variance of a binomial distribution. Our first example is about flowers. Now we have looked at expectation and variance before. We're now just applying it to a different distribution. Okay, so our first example here is a box contains a large number of carnations, of which 1/4 are red, the rest are white. So we've got 1/4 red, 3/4 white. Carnations are picked at random from the box. How many flowers must be picked so that the probability that there is at least one red carnation, this is our R, among them is greater than 0.95. So this is our N. So different than the questions that we did in the last video, because now we're looking for our number of trials instead of our probability. So the first thing that we can do is define our variable. So let's use X again. And in this case, our random variable is the number of red carnations. And we'll write out our binomial distribution. We only know one part of it right now, which is our probability of getting a red flower. The next thing that we're going to set up is our probability statement. So our probability that X is greater than or equal to 1 is equal to 1 minus the probability that X is equal to 0. We don't know what I have to add up to, so I can't use the approach of adding the probability of X is equal to 1, X is equal to 2, X is equal to 3, because I don't know where to stop at. So I have to use the complement approach and find the probability that no red carnations are chosen. So let's write it out using our binomial distribution equation. N, choose R, where R is 0 in this case. We have our probability of success raised to the number of successes. Then we have our probability of failure raised to N minus R, which would be our Q value, our number of failures. So let's simplify this a little bit. First one is N, choose 0. Good example of where you need to be able to apply that factorial equation. So we'd have n factorial over 0 factorial times n minus 0 factorial. Top stays the same. Fun fact, 0 factorial is actually equal to 1 because the number of ways that you can arrange 0 things in 0 ways is 1. It's a good thought-provoking idea there. Okay. Then n minus 0 factorial is the same as n factorial. Those cancel out, and we're just left with 1. Okay, in the same color, I'm going to cross this whole part of our expression out. That also goes to 1, and then that 0 doesn't really matter. So what we're left with here is 1 minus 0.75 to the n. So we also know our probability. We know that this has to be greater than 0.95 or 95%. First thing I'm going to do is some rearranging. So 0.05 has to be greater than 0.75 to the n. Now I need to get that exponent down, and so what I'm going to do is take the log of both sides. What that allows me to do is bring the exponent down in front, and then I'm going to divide both sides by log 0.75. Now be careful, anytime you're dealing with inequality and you divide by a negative value, you need to switch the sign. In this case, log 0.75 is negative, so our inequality sign is going to flip, and we're going to get n has to be greater than log of 0.05 over log of 0.75. And this is going to tell us that n has to be greater than 10.4. Okay? Therefore, we need at least 11 draws to make sure we have at least one red carnation. Okay, so same idea as paint can questions. You get an answer like 2.6 cans of paint. That really means that you need 3 cans. This is the same idea. If n has to be greater than 10.4, the only way to do that is to draw 11 flowers. So that's sort of an extension of the work that we did in the last video about the binomial distribution. What we're going to focus on today is the expectation value. So if you have a binomial distribution characterized by n and p, the expectation of x, or the expected value, is just n times p. So let's take a look at this in an example. A biased dice is thrown 30 times, and the number of sixes seen is 8. The dice is then thrown a further 12 times. Find the expected number of sixes for these 12 throws. So let's let x represent the number of sixes seen in 12 throws. Okay. The next thing I'm going to do is use my experimental data from the question. So I know that P, my probability of a success, is going to be 8 over 30, or 4 out of 15. Because I've thrown the dice 30 times, and I've been successful. I've gotten a 6 8 times. So now I can write my binomial distribution as n. That's the number of throws that I'm now doing, and then my probability of success. Now I can find my expected value as n times p, which would be 12 throws times 4 out of 15, the probability of getting success. Let's reduce a little bit first. You can divide those both by 3. So we should get 16 over 5, which is, I think exactly, which is 3.2. Here's a good example. It came up before. It doesn't have to be a value that's actually obtainable. Okay. Why do you think that is? You can speculate if you want to and put it in the comments for the video. The next thing that we're going to look at is the variance for a binomial distribution. So if x is represented by a binomial distribution characterized by n and p, then the variance of x is n times p times q, where q is 1 minus p. Same characteristics that we had before. So let's take a look at this one in our example. In a large company, 40% of the workers travel to work on public transport. A random sample of 15 workers is selected. So far we've got our probability of success. We have our n. We're going to find the expected number of workers in this sample and the standard deviation. Note, not the variance. Remember that our variance is the standard deviation squared. Okay, like this. Okay. So we are looking for our expected value. Let's switch it up for this one. We're going to define our variable as W, and we'll let W represent the number of workers who travel to work on public transport. So first thing that we want to do is write down our binomial distribution characteristics. We've got 15, and our probability of success is 0.4. So the first thing the question asks us to do is find our expected number of workers. So we're going to do n times p, which is 15 times 0.4, which gives us 6. So therefore, 6 workers are expected to use public transport. The next thing that we're going to do is our standard deviation. So I'll do that over here. So first thing that we can find is our variance of our variable, which is n times p times q. N, p, q. Remember that p and q have to add up to 1. And this is going to give us 3.6. From there, the question's asking us to find the standard deviation of the distribution. Which is going to be the square root of our variance, which is approximately 1.9. So the last thing to note is that the expected value of x is also called the mean. Okay, so sometimes it shows up e at x equals mu. There are 3 sets of homework questions. They all have a couple dealing with different aspects of the binomial distribution.